We think of NASA as having touched the sun. That was the simplified version we all learned with the announcement of the mission. A spacecraft flying close to a giant fireball, dangerous, impressive, but conceptually simple. Then, in 2021, when NASA's Parker Solar Probe crossed a boundary that scientists call the Alfvén surface, something unexpected happened. The spacecraft entered a region that, by its own definition, is still part of the sun. Not near the sun, not around the sun, inside it. In reality, something stranger unfolded. The sun isn't where most of us think it is, and as Parker got closer, the sun didn't appear as a simple glowing sphere suspended in space. For centuries, our mental picture of the sun has been fairly clear: a bright surface, a hot atmosphere, then emptiness. We look up and see a glowing disk sharply separated from the darkness around it. The sun seems to be ending, yet its magnetic fields stretch millions of kilometers into space, and charged particles are constantly flowing outward. The visible surface, in some ways, resembles not the edge of an object, but the upper layer of an ocean whose currents extend far beyond what our eyes can see. This was already understood before Parker launched in 2018. The mission was sent because a surprisingly fundamental problem remained unsolved. Why does the sun's atmosphere get hotter the further away from the surface? Common intuition suggests that heat should decrease as you move away from the source. Stand next to a fire and step back. The temperature decreases. But measurements from telescopes and spacecraft revealed the exact opposite. The sun's visible surface is approximately 5,500 degrees Celsius. Above this lies the corona, a vast atmosphere that extends into space, where temperatures can rise to over 1,000,000 degrees. Scientists could measure this phenomenon, but they couldn't fully explain it. Something was missing from our picture of the sun. Parker was designed to fly closer than any spacecraft had ever reached before. Its orbit gradually narrowed due to repeated gravitational pulls from Venus, entering an environment no human-made object had ever directly explored. Engineers developed a heat shield capable of withstanding conditions that would instantly destroy ordinary spacecraft. But heat wasn't the biggest challenge. The real challenge was entering a region where magnetic fields affect the behavior of matter in ways that are difficult to predict. Previous missions had observed strange disturbances in the solar wind. The solar wind is generally described as a continuous stream of particles flowing outward from the sun. This definition is useful, but it is also incomplete. Measurements showed that the flow contained abrupt reversals, sudden changes in magnetic direction, which appeared and disappeared rapidly. Nobody knew exactly where these structures were forming or why they existed. Then Parker passed directly through them. The spacecraft detected massive magnetic reversals, regions where magnetic field lines bent sharply and then returned to their previous directions. The solar wind was turbulent and twisty instead of a smooth flow. What appeared to be random disturbances were evidence of physical processes operating near the sun's surface. The solar wind doesn't just escape from the sun, it also carries traces of events occurring deep within the sun's magnetic environment. The closer Parker got, the more the sun resembled a system of interacting structures rather than a simple source of light and heat. Then came the crossing of the Alfvén surface. This boundary separates two vastly different regimes. Beyond this, the solar wind moves so fast that disturbances cannot return to the sun. Inside, however, magnetic forces still hold direct control. Information can flow in both directions. When Parker passed through this region, scientists found themselves inside a previously unsampled section of the sun. But the boundary itself was not smooth. It was wrinkled, folded, and constantly in motion. Parker crossed this boundary multiple times because the surface was moving through space. It turned out that the edge of the sun resembled a constantly changing landscape rather than a shell. If even the location of the sun's effective boundary is constantly changing, then the smooth diagrams we carry in our minds conceal a far more complex reality. The sun is not a static object surrounded by space. It is an active system whose influence gradually permeates its surroundings. At this point, another mystery began to emerge. For years, astronomers debated how energy passed from the sun to the corona. Magnetic reconnection, plasma waves, and many other mechanisms had been proposed. Parker's measurements suggested the answer might not belong to a single process. The spacecraft observed intense magnetic activity concentrated in surprisingly localized regions. Tiny structures seemed capable of releasing enormous amounts of energy. Small-scale processes could shape large-scale behavior. The deeper the researchers dug, the harder it became to isolate a single, simple explanation. The laws governing the sun are not mysterious. They are the same laws tested in laboratories and observations across the universe. Gravity, electromagnetism, plasma physics. Yet it is difficult to predict the outcome produced by these laws in detail. Small changes can lead to enormous consequences. Structures form, interact, collapse, and reform on scales ranging from kilometers to millions of kilometers. The sun is not breaking the rules. It is showing us how much complexity the rules can create. Scientific progress is often imagined as a steady march towards certainty. A mystery emerges, data comes in, the mystery disappears. Reality is often less collaborative. New measurements often solve one problem while revealing several others lurking behind it. Parker's mission followed precisely this model. It answered questions about the position of the Alfvén surface and revealed details about magnetic spins. But each answer revealed additional layers of complexity. How exactly is energy transferred across the corona? Which processes are dominant under specific conditions? The closer we got to understanding, the more structures beneath the surface were revealed. And perhaps this is Parker's most surprising lesson. The sun was never a gigantic glowing sphere sitting at the center of the solar system. This image was useful because it compressed something incredibly complex into a form our intuition could comprehend. But when a spacecraft finally entered the sun's outer atmosphere and began to measure it directly, we realized we were wrong. Beneath the apparent simplicity were shifting boundaries, complex magnetic landscapes, hidden structures and processes operating on scales that are almost impossible to visualize. The mission didn't reveal that everything we knew was wrong. It revealed something more interesting. The closer our measurements get to reality, the more reality seems to resist simplification. And if something as familiar as the sun can still surprise us after centuries of observation, then perhaps the greatest limitation in our understanding is not what we do not yet know, but our tendency to confuse a useful picture with the thing itself.